Good morning, everyone. I will talk about my recent research project titled as Scheduling when the system accepts random arrivals. So, this is a joint work with Professor Peter Taylor and Dr. Mark Fackrell. We all are tired of waiting in queues. In our research, we are attention to reducing customer waiting cost and server idle cost by using scheduling. So, this system we consider has a one server. Our objective is to find out the optimum schedule for capital N customers, which minimize the total expected cost of waiting for both scheduled customers and random customers. Our service rate is mu, and we have Poisson random arrivals with rate lambda. If we look at the service policy, we give non-preemptive priority to scheduled customers. So if we have the scheduled customers arrival, what we do first is we look at the server. If there is a customer who is already being served at the server, we first finish that service despite the customer is a random customer or a scheduled customer. If we can finish that service before the I plus first scheduled customer's arrival, then we start serving scheduled customers in the system. Again, if we can finish those services before the I plus first scheduled customers arrival, then we start serving random customers in the queue. So that is how we are going to serve the customers who arrive at the system. So this system starts at the first scheduled customer's arrival, and we close the system at the last scheduled customer's arrival. At the last scheduled customer's arrival, we stop accepting random customers and continue to serve what we have at that time until we finish all the customers who are already in the system. So if you look at this inter-arrival time between two consecutive scheduled customers, we can see that there can be infinitely many possibilities can happen during that time interval. Considering that the probability of occurring something during a very small time period, we truncate it into few cases, and we all know that the upper bound of the Poisson process is infinity. In this case, we consider capital M, which is a finite positive number for the upper bound for the Poisson process. So what we do is we consider all the possibilities that can happen during this time period to write down our cost function. So this is the Laplace transform of our cost function. This Ri, Ki, Mi, Li represents the cost from the I scheduled customer's arrival until we close the server. So if we can write down the R1, K1, M1, L1, that is the cost function at the first scheduled customer's arrival, then that represents that gives us the total cost of the total expected cost of the system. So we use some numerical values and simplify this expression, and then we do the optimization. Here we have done it for two customers. So this result is for scheduling two customers with service rate equals 10. And we use several lambda values. You can see that when we increase lambda, that means when we increase the rate of random arrivals, the inter-arrival times are getting decreased. That means when the possibility of a random customer's arrival is getting higher, we try to schedule customers more frequently. This same thing happens when we increase capital M, which is the upper bound of the Poisson process. That also increase when we increase M, that means we increase the possibility of random arrival. So in that case also, the inter-arrival time is decreasing. So that is the end of my presentation. Thank you for listening.